This is a flexible fiber optic borescope available in the NDE laboratory. It's about 10 feet long and has a flexible tip at the end with a 45-degree mirror so that it can look sideways. The operator looks through the eyepiece to see the image while simultaneously turning the control knob to make the tip flex one way or the other. This particular borescope is unique in that the light source can be switched between white light and ultraviolet light. The ultraviolet light can be used to perform fluorescent dye penetrant inspection inside places that are very difficult to access otherwise. Here is a fiber optic borescope with a different design. It has replaceable tips on a long, flexible light and fiber optic source, and the display is shown on a television. The tips can be easily replaced and changed for a wide variety of different probe tips. This one has a right angle bend and is rigid. Other tips can be rather flexible, maybe only a couple millimeters in diameter, and yet with a lens on the very end can image even fine print on a business card. Here are some images as seen through the borescope on the television. These are images of the business card, and these are images taken on a barrel. This is a liquid penetrant inspection station. There are various stages to the inspection. The first is a dip tank to immerse the parts, a drain tank to let the penetrant drip off, a washing station to wash the excess penetrant off, a dryer to completely dry the part, some powder, white powder to develop the flaw indications, and finally an ultraviolet black light. This is a wet horizontal magnetic particle inspection machine. It consists of a headstock and a tailstock. This is the tailstock you see there that can be used to inject current through a part, or a coil that you see here to induce magnetism in the part. The hose carries the penetrant, and the thing with the green handle is the ultraviolet black light. Let's back off a little bit and get a bigger view of the whole thing. There's a hood that can be pulled over so that you can see the black light under dark light. This is the roll scan instrument manufactured by American Stress Technologies. It uses the magnetic Barkhausen noise effect to detect the presence of grinder damage. Special purpose probes with an alternating magnetic field induce the magnetic Barkhausen noise, which is detected essentially by an eddy current coil. This is an eddy current machine manufactured by IBG. It uses 8 simultaneous frequencies to measure the eddy current response of a part. It can be trained by presenting it with known good parts. It statistically determines the eddy current response at all 8 frequencies to those parts. Here the machine is being presented with a bunch of bolts, all known good. Once the machine has been trained, it's then possible to present the machine with parts, and it'll make a decision whether it's like all the previously seen parts or something completely new. It's especially useful to have this approach where you don't have to have known bad parts in order to set up the machine. If there's anything wrong with any one of the 8 frequencies, it'll give you the red light and show you which of the 8 frequencies was responsible for calling it a defective part. As you can see, as he's placing parts through here, the machine is rather fast and can be usually placed in a production environment for 100% automatic sorting of known good from known bad parts. Eddy current technology is especially useful for sorting for wrong material or improper heat treatment. Here's an IBG machine in use at the fuel systems plant, sorting barrels for improper steel. It has two coils. The one on the left holds a reference part, and the one on the right is for the test part. This helps balance the system so it can see very small changes in eddy current response. Again, as before, the machine either gives a green light or red light, depending on whether the eddy current responses are the same or not. This is a close-up view of the instrument, showing what the instrument response looks like between good and bad parts. This is an IBG eddy current machine especially designed for crack detection. Crack detection is different than a material sorting application because the probe has to be scanned past the flaw to detect it. This is the cracked part in a lathe with a probe attached next to the spinning ball end of the part that has the crack. Each time the crack goes past the probe, there will be a jump in the eddy current response of the instrument. This is the real-time radiography system in the NDE laboratory. Basically, it's just a lead-shielded box with an X-ray tube, manipulator to move the parts, and an X-ray detector. Here we see the view inside the enclosure. The X-ray tube is there. It's fairly high voltage, rather small spot size. You see the manipulator bringing our object in from the right. We're inspecting an alarm clock. The manipulator may translate the thing to the left and to the right, vertically up and down, towards the door and away from the door, and also rotate the part. This particular object was chosen because it has some internal moving parts that you can watch in real time. Here we can see our part on the manipulator and the image intensifier tube, which detects the radiation. This is an example of what that alarm clock looks like on the real-time radiography system. You can see all the hands and internal gears and springs moving. The actual monitor is much higher resolution than this, and you can actually see the little spring on the balance wheel wind up and unwind. This is the X-ray facility at Body Coat in Indianapolis, where we're inspecting some aluminum heads. It's basically just like the real-time radiography system, except that it's much larger, much higher power, and they use film instead of a fluorescent screen to get the image. Let's go inside and take a little closer look here. The parts are laid on a turntable so that they can orient it with respect to the X-ray generator, which is suspended from the ceiling. The controller is outside the room, so there's nobody present when the X-rays are being generated. Here's a close-up of the parts. We have a bunch more on the floor ready to go as well. That's a little closer view of that X-ray generating tube. This is an X-ray diffraction machine used to measure the residual stress in parts. There are 3 X-ray diffraction machines in Cummins. This one's made by American Stress Technology. The other 2 are made by Technology for Energy Corporation. This one's at the Fuel Systems. There's one at Jamestown and one at the Tech Center. The head emits X-rays, and there's a little detector on the side that detects the diffraction of those X-rays, which is measured as a function of the angle with respect to the part. All this information is gathered, and the end result is to essentially calculate the spacing between the atoms, which is related to the residual stress. This is the ultrasonic immersion C-scan system in the NDE laboratory. It can be used for a wide variety of ultrasonic tests. It consists of a tank of liquid, which is the couplant, a bridge and search tube, which holds the transducer. It can be moved in many different dimensions relative to the part. It can be moved in X, Y, and Z directions. The probe itself can be angled in 2 directions. And as you can see in this case, we can rotate the part on a turntable. Once the part is in place, the transducer is moved over the bore, lowered into place, and then spun. As the part spins, the transducer will be incremented up for each turn of the connecting rod. The echoes from the back surface of the bushing are gated and plotted versus the position of the transducer, yielding a map showing the location of non-contact between bushing and rod. This is another application of ultrasonic inspection. An instrument is made by Kramer, and the probe is special. It has 2 sensors in it that launch a surface wave on the material, measure the velocity of sound on the surface, and from that compute what the longitudinal velocity of sound through the thickness would be. And then it can be used to measure the thickness of a part without knowing ahead of time what the velocity of sound was in the part. So you could use it to switch between copper, aluminum, steel, cast iron, etc. This technology will be important to Cummins looking for whether we have CGI iron or not. For now, I'd just like to take a little break from NDE, take a little tour around Columbus and Cummins. Sit back and relax.